Okay, now in example 3 from the previous video, we showed how we can reproduce the results of a game with a saddle point if we use this new language where we describe strategies in terms of vectors. This 1, 0 represented the fact that the row player would always choose row 1. This 1, 0 represented the fact that the column player would always choose column 1. Right? Now it turns out that the same thing works when you have mixed strategies. Now in the book they do this in general. I think it's better to take a look at a specific example. So here's a specific example. Also, oops, not that one. That's not what I want. I want is this one. Here's a specific example of a game where you have Jones and Smith, and Jones either pulls out a $1 bill or $2 bill, and Smith makes his guess. And if Smith guesses correctly, he gets the money, and if he doesn't, he gets nothing. So let's look what happens when Jones uses a mixed strategy of 2/3, 1/3. That means 2/3 of the time he pulls out a $1 bill, and 1/3 of the time he pulls out a $2 bill. Now remember that this matrix here is G, and we've been talking about P0 times G. Now if I take P0 times G, that's going to be 2/3, 1/3 times G, and G is going to be minus 1, 0, 0, minus 2. And you do your matrix multiplication and you end up with minus 2/3 and minus 2/3. Now, what do these minus 2/3 represent? Well, this minus 2/3 represents the average payoff to the row player if Smith always guesses 1. If Smith always guesses 1, what's going to happen? Well, 2/3 of the time he's going to be right, and 1/3 of the time he's going to be wrong. When he's right, the row player loses $1, and when he's not right, he loses nothing. So his average loss is going to be minus 2/3 of $1. You could think of it this way. If they played this game 30 times, and row player uses this strategy, and column player always chooses 1, out of those 30 times, on the average, 20 times he'd guess correctly, and 10 times he'd guess incorrectly. So he'd win $20. $20 out of 30 times you play is average of 2/3. So his player Smith would, on the average, gain 2/3 of $1. Jones would, on the average, lose 2/3 of $1. So this represents his average losings. We could say average winnings. His average winnings is negative because he loses. Similarly, if Smith always guesses the $2, then what's going to happen? If Jones uses this strategy and guesses $1 bill 2/3 of the time, $2 bill 1/3 of the time, then Smith will only be right 1/3 of the time. So out of, say, 30 times they play the game, Smith will be right 10 times, but each time he guesses right, he gets $2. So out of 30 game plays, Jones loses $20. So minus 20 over 30 gives an average losing of minus 2/3, or average winning of minus 2/3, average losing of 2/3 of $1. All right? So these express the average winnings. This is the average winning if C chooses 1. And this is the average winning if C chooses 2. All right? Now let's do the same thing with Smith. Smith, if we take Smith, we're saying that G times, in this case, his strategy is also 2/3, 1/3. All right, that's what we said. I should just write that's G times Q0. Right? Okay. All right. And so that's going to be minus 1, 0, 0, minus 2 times 2/3, 1/3. And we end up, in fact, with the very same thing. In this case, we get minus 2/3, minus 2/3. Now I could go through the same argument. This expresses the loss of what's his name? It's Jones that calls Smith. The loss of Smith, if the average loss of Smith, if he always chooses column 1. And you just use the same argument. And this represents the average loss of Smith if he always chooses the $2. Okay, go through the same argument. Now it's a negative loss, so that's going to be a net gain for him. Now notice that all these values are the same. And that accords with this definition here, that if we get this value where the P naught G is greater than or equal to VE and GQ naught less than or equal to VF, that's true in this case. So the value of my game is minus 2/3. And if Smith and Jones use this strategy where each chooses $1 with probably 2/3 and $2 with probably 1/3, then Jones will guarantee the best minimum average payoff, and Smith will guarantee the best minimum of his maximum loss. Right? So it's kind of extension of the first case where you had a saddle point, only you do the same thing with mixed strategies. Where linear programming comes in is to determine these mixed strategies. I haven't told you how I got these values. That's where linear programming is going to come in. So let's do another example here. This one is also from the book. And in this case we have this matrix. You can verify that there's no saddle point. And the two strategies we're going to look at is P0 is 1/7 6/7 and Q0 equals 6/7 1/7. So in this case the two strategies are not the same. I don't want you to have the impression that P0 and Q0 are always the same. Right? So let's look at P0 times G. Okay, that's equal to 1/7 6/7 times 10 minus 50, 0, 10. Right? And if you work that out, you're going to get 10/7 and 10/7. Now what's the interpretation of this 10/7? Well, if player Mr. Sub uses this strategy and Mr. Super chooses favorable every time, then whenever Mr. Sub chooses favorable, he wins 10, and whenever he chooses unfavorable, he wins 0. So 1/7 of the time he's going to win 10, 6/7 of the time he's going to win 0. If you work out the computation of this 10/7 here, this 10/7 is 1/7 times 10 plus 6/7 times 0. Okay? So in fact this 10/7 is going to be in the long run his average winnings if Mr. Super always chooses favorable. Right? Now how about the other entry here, 10/7? Well, if Mr. Sub chooses favorable with probably 1/7 and unfavorable with probably 6/7, what's he going to win on the long run? Well, 1/7 of the time he's going to win minus 50, which is bad. And 6/7 of the time he's going to win 10. So 1/7 times minus 50 plus 6/7 times 10 gives me, again, 10/7. So this 10/7 is the long run average winning of Mr. Sub if he uses this mixed strategy and Mr. Super uses either strategy. Now notice that here it doesn't matter what strategy Mr. Super uses. Whatever strategy Mr. Super uses, he's going to use 10/7. In fact, even if Mr. Super uses a mixed strategy, still Mr. Sub on the average is going to get 10/7. That's his guaranteed value. And let's do the same thing for Q0. If I take G times Q0, that's equal to 10 minus 50, 0, 10. Okay, this is times 6/7, 1/7. And you can work out that you get, in fact, the very same result. You get 10/7 and 10/7. Okay, So if Mr. Super uses this mixed strategy, he can guarantee himself, no matter what strategy Mr. Sub uses, he can guarantee himself an average winning of 10/7. Now, if Mr. Sub uses this strategy and Mr. Super uses any other strategy besides this one, then Mr. Sub can gain an advantage. On the other hand, if Mr. Super uses this strategy and Mr. Sub uses any other strategy, then Mr. Super can gain an advantage. This mixture of strategies guarantees each person the best possible long-run average winnings. All right, so this corresponds to your saddle point in the strictly determined games. All right. So here there are some theorems about mixed strategies that I'm not going to show the proof, but because my focus is on linear programming, but at least you should be aware of them. First theorem says that if G is a matrix game that has a value and optimal strategies, then the value of the game is unique. There's only one value. Can't have two values. This is similar to the question that a game cannot have two saddle points. Okay? There's only one. A strictly determined game can only have one saddle point. And a game with mixed strategy and a value can only have one value. Okay. Another theorem. G is a matrix game with value V and optimal strategies P0 and Q0. Then V equals P0 G Q0 P0 G Q0. This is related to the fact that no matter what strategy the Mr. Super uses, Mr. Super strategy would correspond to a column vector multiplying this row vector. No matter what column vector Mr. Super chooses, you're still going to get a 10/7. Right? If I multiply this row vector by 6/7, 1/7, I'm going to get 10/7. Doesn't matter what. If I multiply this row vector by any probability vector, I'm still going to get 10/7. All right? So that's what this theorem is about. And then let's see, one more theorem. If G is a game with value V and optimal strategies P0 and Q0, then V is the largest expectation that R can assure for himself. Similarly, V is the smallest expectation that C can assure for himself. This is what I've been saying about the maximin and the minimax. V is the maximum minimum payoff for the role player, and V is the minimum maximum penalty for the column player. All right. So that's kind of background of general game theory. Soon we'll see how to apply linear programming to find these optimal mixed strategies.